Welcome everybody again, and thanks to the speaker Javier Martínez, who is going to talk us about the representation varieties and Alexander type invariants in knot theory. Thank you very much for giving us this talk.
Okay, thanks Marina for the invitation. It's a pleasure being here and having the opportunity to give a talk in the seminar. So, okay, the title is Representation Varieties and Alexander type invariants in knot theory. And what I'm going to discuss is joint work with Vicente Muñoz and Gonzalez-Prieto. It's a preprint that we've uploaded a month and a half ago or so. So all the details are there, okay? So what are the goals or the main objective of the talk, okay? Alexander invariants, and by Alexander invariants I mean the Alexander polynomial and the Alexander module. We're going to review some classical definitions, and the main goal, the first goal, is to provide an interpretation entirely in terms of representation theory. We'll see what this means, okay? Exactly how representing its knot group onto the AGL1, which is the group of affine motions of the complex plane, recovers and unifies many treatments or many things related to the Alexander polynomial. So on itself, it's a treatment that I think that unifies several classical things. And then, apart from unification, we'll use it to construct a TQFT that computes those Alexander invariants. So I'll say what we're working on right now, but it gives new formulas and new ways of thinking about the Alexander polynomial. And this is pretty much the outline, the way the talk I'm going to structure it, okay? I'm going to start describing what I mean by representation varieties, by character varieties, especially focusing on knot theory. And then that section 2, I'm going to discuss, give a brief introduction to the Alexander polynomial and the Alexander module. And then 3 and 4 will focus on this tree, okay? So, okay, representation varieties. Well, many people here in the audience already know this and are currently studying these spaces. But in full generality, you pick any finitely generated group, gamma. Down there in the gray box, you pick a finally generated group with R generators and then certain set of relations. And then the space of all representations of your gamma into G, where G is a Lie group, complex, real, you've got several modifications. For me, it's going to be, full generality, a linear algebraic group to do algebraic geometry. And then the set of all homomorphisms of gamma into G, that's what we call the representation space of gamma into G. And then you've got an obvious or standard action of G on that space of representations by conjugation. If you think that G is a matrix group, a linear group, it's simply codifying that you're going to consider two representations equivalent anytime you're changing your basis, okay? So you want to declare conjugate representations, that G is acting on all the elements of the representation simultaneously, and you're going to consider those two representations equivalent. So in a straightforward definition, you've got your gamma and then the representation space of gamma into G. Simply you pick R matrices, which correspond to the generator, satisfying those relations, and those relations are going to give you the algebraic equations defining that algebraic set. By variety, I'm not talking about irreducible, and it's standard in this topic. It's simply an affine algebraic set. That representation space inherits the structure that G has, okay? The main focus, G is going to be AGL1, we'll define it later, and gamma is going to be a knot. And then the character variety, which we won't deal much with it today, is simply the appropriate quotient in the setting that you need by that conjugacy action. So if you want to construct an algebraic variety, which the representation space, you've got certain problems. For example, the quotient is not a Hausdorff space. And then the standard way of doing that, if Rg, which is an affine algebraic set, is the spectrum of a certain ring, then picking G invariant functions, and by G invariant I mean the action of G by conjugation, the spectrum of that ring defines a quotient in the algebraic set. And the quotient prescribed by geometric invariant theory. In this case, everything is affine, so it's really straightforward. And it's a GIT quotient. Topologically, you're basically identifying certain orbits you're identifying those orbits whose closures intersect. And then, thinking about functions, the coordinate ring of invariant functions, that's the coordinate ring of the representation space, is in most cases generated by trace functions. What do I mean by trace functions? You pick any element of your finitely generated group, gamma, and then any representation, you can always evaluate that representation on gamma, then you can take the trace. That rho of gamma is an element of G, and then you can take the trace. Obviously, that function is G invariant. It's invariant by conjugation because it's defined by a trace. And those trace functions can be proved that the ring of invariant function is generated by trace functions. Okay, and then you also have the inverse. This is pretty much the general picture. And then knot groups. Okay. In knot theory, character varieties have also been studied in the last 40, 50 years, so it's also a classical topic. And now let's specify. Gamma is the knot group, and by the knot group, I mean the knot inside S3, the fundamental group of the complement is what we call the knot group. And then it usually has been studied when G equals SL2C or PGL2C. And that's the character variety that has been most studied in the context of knot theory, and the definition is the one I just gave, representations of the fundamental group of the complement into G, and then you move out by the G action. And well, the main reason probably is hyperbolic geometry. Knots can be classified into torus knots, hyperbolic knots, and satellite knots. And hyperbolic knots are those such that the complement S3 minus K admits a complete hyperbolic structure. And then defining a hyperbolic structure on that complement, since PGL2C is the group of isometries of the hyperbolic 3 space, is equivalent of defining a representation of pi1 into PGL2C. So that hyperbolic structure corresponds to a specific point in your character variety. That's called the holonomy representation. And it's also known that that specific point belongs to a component, and actually that point is a smooth point inside your big character variety. And then I'm not gonna revisit these topics, but many things have been done. You can define knot invariants such as the A polynomial, which is a polynomial in two variables, which is defined looking at a certain subgroup of pi1, which is the peripheral subgroup, and looking at the eigenvalues of the representations of the peripheral subgroup. And then the geometry and the topology of the free manifold S3 minus K, the complement of the knot. Several works related, for example, ideal points, they're called ideals. You need to pick a component and then projectivize and so on, and related to surfaces in your free manifold, and then geometric structures, like I said, for other groups different to PGL, codify geometric structures on your free manifold. So it has been an extensive topic of research in the last years, also in knot theory. Okay. Now something which I'd like to introduce and to remind now, because we're gonna use it later. Okay, this is usually covered in any introductory knot theory course. Okay, the knot group, which I have stated before, if you pick an oriented knot and then you've got a planar projection, that one there is a planar projection of the threshold knot. Okay, it's gonna be the example we're gonna move around to compute things. Admits or can be, or you can get a presentation of the fundamental group of S3 minus K, the knot group, with n generators and n minus 1 relations corresponding to the following thing. You can choose a generator of the fundamental group of the complement, one for each arc of your knot. So there the threshold, you've got one there, another one there, and another one there, where when you go or pass through an undercrossing, then the generator changes. That's the picture, the three-dimensional picture there. You've got one there, that's the overcrossing, and then you've got two there, which when you pass an undercrossing. And then the relations are called Wirtinger relations. This is called a Wirtinger presentation of the knot group, are conjugacy relations. There are two types. type 1 or type 2, positive or negative, according to the orientation of the strands according to the right-hand rule. So for example, that's a positive, because if you graph the overcrossing strand, that's positively oriented, and the other one is negative, okay? And now here, xi plus 1, we're changing generator because that's an undercrossing, and xj, which is the overcrossing strand, it's another generator of your fundamental group. So the goal, just to remember that node groups can be explicitly described or presented using generators for those arcs, and then the relations are conjugacy relations. This is the ultimate representation of any of node groups, okay? And then this is not a within representation, but I thought, okay, let's include an example. For example, if you pick a torus node, people in the audience are studying these nodes for SL4C and other groups, okay, which is a much harder problem, but a very readable paper Vicente wrote it in 2009 or so. It's in Revista Matemática Complutense, studies the SL2C character variety of torus node. That's a different presentation. It's an easier one because you only have two generators in one relation. Okay, that's also a presentation for the node group. And leaving aside all the considerations, character varieties, I mean, are an object of study by themselves. You might wonder, okay, what geometry, or what structure, what topology does this space have? Pairs of matrices satisfying a very simple equation such as A to the M equals to B to the M. And now that's a torus node. I haven't mentioned them, but basically you grab a standard torus, you pick a line of slope P divided by Q, and then that line winds up the torus, and the curve that you get is a PQ torus node. Okay? The trefoil is a particular case, it's the 3-2 torus node. And this is the character variety. In this case, it's simple, but even in the simple case, you can check that it's not irreducible. You've got a bunch of components. There's terminology here. You've got reducible representations, which are representations such that all the matrices share a common eigenvector, so you can conjugate them to get an upper triangle matrices, and then the reducible locus is the other ones. In this case, that component is C. This is simply a schematic picture, okay? Because basically reducible representations are codified by eigenvalues, and then you need to mod out by the conjugacy relation, but you get that all the eigenvalues can be controlled by this, and then you get a bunch of irreducible components. There are 1/2 P minus 1 Q minus 1 of them, and they are controlled. It's a discrete set controlled by roots of unity. It's a nice exercise, and then each of them, the parametrization is given by a cross ratio. So it's really readable. If you've never heard of character varieties, promise that one can be is quite accessible. Okay. Okay. Yeah. So that's on one hand, character varieties and representation spaces. And then I'm gonna quickly revisit the Alexander polynomial, okay, and the Alexander module. It's almost 100 years old, okay. It was introduced in 1928 by Alexander, and then I'm gonna give some facts, some examples, and then one definition. It was the first non-trivial node polynomial invariant. Okay, it was thought that it was the only one until the arrival of the Young polynomial. And it's not really a polynomial, it is, but it's an element of that ring, Z over T, T minus 1. Sometimes it's defined as a Laurent polynomial, okay? It's a polynomial in T and 1 over T. And I say that it's not truly a polynomial because it's not uniquely defined. It's always defined up to a multiplication by units on that ring, okay? The units on that ring are powers of T. So you can multiply that polynomial by T to the n, and you still get the Alexander polynomial. So you've got several normalizations of the Alexander polynomial. One of the most common is to normalize it so that when you inverse the T, you get the same polynomial, the same Laurent polynomial, and then the Alexander polynomial of the unknown is 1, but there are several others. For example, another one is to normalize it so that you've got a polynomial and the constant term is positive. So there are several. It's not a complete invariant, okay? For example, it's defined from an oriented node, but if you switch the orientation or you take the mirror of that node, you get the same polynomial. And well, I mean, we've got 100 years of research. It's connected to many, many other topological invariants, such as the genius, and it's one of the core topics in knot theory. Two tiny examples, they are not, I've already said that the polynomial is 1, and then the trefoil Alexander polynomial, t plus 1 over t minus 1. It's following that normalization, but we can also use, for example, t squared plus 1 minus t. We multiply that polynomial by t. Okay, so it's not uniquely defined. And how does it arise, or how can you define the Alexander polynomial? Well, one of the most classical approaches is you've got your knot group, and then you can take the commutator subgroup. Okay, and that commutator subgroup is a normal subgroup of the fundamental group. So it gives rise to what, by the theory of covering spaces, to a normal or a Galois covering space, which I'm gonna call X tilde. Okay, that in knot theory is called the infinite cyclic cover. Okay, it's a covering space of X, and the group of deck transformation, which in covering spaces theory is a set of homomorphisms of X tilde compatible with the projection, that is the projection invariant, is isomorphic, that's why infinite cyclic, to set. And we're gonna fix T for the generator of that set of infinite of deck transformations. Okay, view quotient, and that's gonna be important. Pi 1 by the commutator subgroup, you're abelianizing the fundamental group. And if you think of Wirtinger, okay, the type of relations that were there, which are were conjugations, if you abelianize all those relations, you get trivial relations. And then, since all the arcs are conjugated, it can be proven that H1 of the knot is generated by a single meridian. Okay, so the first homology group of the knot, of the complement of the knot, sorry, is isomorphic to set. Okay, it's generated by a single element. And then those deck transformations, they are generated by a single element. So you've got a T, an element which is acting there by homeomorphisms. Okay, so it induces an action on X tilde, on the homology groups of your infinite cyclic cover. So the recipe is you've got X, you've got your free manifold, S3 minus K, you've got the commutator subgroup that defines an infinite cyclic cover with group of deck transformations isomorphic to T, to Z, sorry, with a generator T, and then that acts on the covering space, it acts on homology. So naturally, the first homology group is a module over that ring, because you've got a T action on homology. Okay, so that guy there, this module is what is called the Alexander module of the knot. And then the Alexander polynomial, I'll revisit the definition in a while, is the order of that set T minus 1 module. Okay, that's the algebraic definition. And now it can be defined using many other tools. Okay, it can be defined, and I'm going to revisit this. You'll see why, because it's related to representations, which is our goal today. Okay, to Fox calculus, which is a way to obtain a presentation for that module. Okay, a presentation matrix for that module, starting from the knot group, but also topologically. Okay, it's quite classical to grab your knot, to build a surface, which is a surface whose boundary is the knot, and from there, topologically, to build a certain matrix, and then the Alexander polynomial is defined as a certain determinant. Another one, which has been really, really important for other invariants, is that it satisfies a scaling relation. That L plus and L minus and L naught is you pick your knot, okay, you pick any of its crossing, and then you can flip a positive for a negative crossing, okay, you simply switch it, and you get a different link. So you start from a positive one, then switching, you get a negative one, a different link, which we call L minus, and then breaking apart that crossing, you get another one, which we call L naught, okay? So they satisfy this kind of recursive relation. You see T to the square root of T. So again, you need to properly normalize the Alexander polynomial so that this holds, but again, and then it can be proved. This was, in fact, that already, it appeared in Alexander's original paper, and but nobody used it until several other years ago, until Conway, who realized that that was quite important. Okay, so the Alexander polynomial is the only polynomial invariant satisfying this relation, and the other normalization that the polynomial of the unknown is 1. Okay, so this allows you to compute recursively the Alexander polynomial, simply applying repeatedly this relation. And then modern approaches, such as knot flow homology, also get you back again the Alexander polynomial in a very different way, but it's also linked to modern theories in knot theory. Okay, and then let me give you a quick definition of how to compute the Alexander polynomial. You've got a module, an R module, where R is Noetherian. For us, M is H1 of your infinite cyclic covering, R is that ring, okay? And then a presentation is a short exact sequence like this one, okay? And A is a matrix presenting your module M, okay? So that matrix with coefficients in R, if you take the n times n minus, okay, the biggest minus that you can get there, the order is any generator of the smallest principal idea containing those minors, okay? And then using smaller minors, you can also define another elementary ideas, which you're not going to get there. Fox calculus is a systematic way to obtain an Alexander matrix for any knot, okay? And we're actually going to compute the Alexander polynomial of the threshold, okay? Just to show you that this approach, okay, now I'm not going to give any hint on why it's true, okay? You need to build a certain cochain complex for the infinite cyclic covering and work details out, but we're going to compute the Alexander module of the threshold, okay? So let's go proceed step by step. Let's start by the definition of the Fox derivative, okay? Pick the free group on n generators, those x1 to xn, okay? And then the Fox derivative is the following set module map, okay? Think first, forget about that set, was a map from the free group to the free group. And then it's a derivative because of the following, okay? The derivative of 1 is 0, that makes perfect sense, of the trivial word, the unit. And then the derivative of xj of any generator with respect to the other, to any other, is the Kronecker delta, which also makes perfect sense. And now the main difference is that the derivative of a product, it doesn't satisfy the Leibniz rule. It's the derivative of the first times 1, so not times the other. And now the first times the derivative of the second one. So there's a certain asymmetry here with respect to usual derivatives, okay? I promised that we were gonna do examples, okay? So that word there is a Wirtinger relator, okay? The xi plus 1 is usually on the other side. So the relation is this equals 1, okay? And now it's essentially reconfiguring your mind and applying that property, those properties, instead of ordinary derivatives. So let's compute the derivative with respect to xj. Derivative of xj with respect to xj is 1 plus xj, the derivative of what's left. That derivative there is 0, so we forget about it, and then it survives, so it's xj, xy. And then when you need to compute the derivative of that product, this is a difference with respect to ordinary derivatives. The derivative of xj to raised to minus 1, it's minus xj raised to minus 1. You can see this clearly. If you pick xj inverse equals 1, you compute the derivative, you apply that, and then you get that it's actually that one. And then the final derivative surviving there, it's 0 because of property 2. So you get that guy there, which right now doesn't say much. And those are the 3 derivatives that are interesting, okay? We did the one there on the middle, and then if you pick the derivative of that word with respect to xi or with respect to xi plus 1, you get those expressions, okay? So what is Fox's main theorem regarding Fox derivatives? It's the following one. If you've got your knot group, okay, and you've got a presentation, the Alexander matrix, a presentation matrix for the module, the Alexander module can be obtained as follows, okay? You compute your Jacobian, which is simply you grab those relations and then you compute the derivative of every possible relation with respect to each of the possible variables. Then there's a first projection which says, okay, you did it for the free group, now do it or projected onto your group, consider the relations that were already there. And then the final step is to abelianize a projected, compose the matrix that you have, abelianize each edge, okay? And then let me go back. As I said, okay, abelianizing the node group, there's a single generator, so everything gets mapped to the same element in a model, so it's T. So that xj, when you abelianize it, it's T, you get a single generator in the homology group. So every xi gets mapped to T. That's T squared, T inverse. You get 1 minus T, and then you get minus T squared, T minus 2, you get minus 1. And I've spent some time, okay, to show you that essentially the relations that appear on those matrices, since the node group is presented using a Wirtgen representation, all the equations look like this. It's always the same equation, okay? Those xi are generators of the H1 of the module, okay, of the Alexander module, and the relation, which are those are the entries of your matrix, are like this one, okay? And as I said, the abelianization is generated by T. So, as promised, let's pick the trefoil node, okay? 3 generators and 2 Wirtgen relations, okay? You've got it there, and then you get 2 equations, which are the previous equations that give you a presentation matrix for the trefoil node. To guide you a little bit, that x1 is that minus 1, the one that it's conjugating, the x2 is 1 minus t, and the one that it sits in there, which is the incoming arc that goes downwards, is that t there, and there you go. And then the Alexander polynomial, once you got the presentation matrix for the Alexander module, you pick any 2 by 2 minor. This is our principal ideal, and that has to be shown that it's a principal ideal. And then you get the polynomial I told you about, which is not properly normalized, but you can always normalize, and we get the polynomial that we saw before, okay? And this is the Alexander polynomial of the trefoil, okay? So Fox derivatives from any presentation of the node group gives you a straightforward way to generate or to give a presentation matrix for the Alexander. And now, some tiny digression, because it's going to appear later. I'm going to go through this quite quickly, okay? There's another topological invariant, much less known, okay, which is called a quandle. Algebraically, a quandle is a set with a binary operation satisfying those properties, okay? It's idempotent, then there you've got some sort of right inverse, okay? So if you fix x and z, you fix an element there and there, there's a unique y satisfying the whole relation, and that may be used to define, that can be inverted to define another operation, which is the triangle pointing in a different direction. It's some sort of inverse to that operation, and then it satisfies a certain distributivity law, okay? Let's jump into the examples. The thing to keep in mind, well, you can always make things trivial in mathematics. Let's forget about that. Line 2 is, for those of you who have never heard about quandles, the thing to keep in mind, okay? Quandles is a way to codify the main and the core properties satisfied by conjugation. So if you pick a group and you forget about the group structure, about all possible products, and you restrict yourself to conjugations, okay? The quandle operation x acting on y is x conjugating y. And then those properties make much more sense, because conjugating x by x, you get x again. Conjugating y by x and getting another element, you can invert the whole thing conjugating by x inverse. And then if you conjugate z by y and then conjugate by x, plugging in x times x inverse where it's needed, you get that distributivity property. Okay, so the best way to remember that is that they are summarizing the properties of conjugation. Yeah, and then why are they important in this context? There's a node quandle that can be attached to any node, and then that gives already a hint, has appeared somehow. On C, you can define an Alexander quandle, which is some sort of complex combination, linear combination of 2 complex numbers, okay? And that operation there satisfies your properties. And then, what's the node quandle? Well, given any node and any planar projection, you can define a quandle in a similar way you define a presentation for the fundamental group. You pick the arcs as generators, and then those conjugacy relations that appear when you're building the node group, that's the quandle structure you're gonna introduce. So there's also a theory of finitely presented quandles in terms of generators and relations, and it works out pretty much the same way. And geometrically, and this is also important, it can be described as the set of homotopy classes of paths from a fixed point of the exterior of your node to the boundary of a tubular neighborhood of the node. I'm going to show you a picture, okay, in a while, but the idea is that it can be represented geometrically as a set of certain homotopy classes of paths.
Yeah.
Yeah.
Xj is over separation of xi and xi plus 1.
Yeah, the xj, it's like acting on xi. In the same way the xj was conjugating xi in the Wittinger relation, so here the quandle structure is xj acting on xi, or triangle xi is the other one. So you can get finite presentation. I mean, it's a finitely presented quandle. There's also that theory. The thing is, and it's quite striking the first time that you see it, is that the node quandle is a complete node invariant up to orientation. And this is a theorem by Joyce and Javier from 50 years ago. Okay? So it's a powerful invariant. Looks a lot like a group. Okay, I'm just gonna mention this, but it's actually stronger than the node group. There are two operations here, and this is going to appear later on, but the main idea is that if you've got a group G, okay, you can build a conjugation quandle, which is what I told you before. Simply, you define the quandle operation to be conjugating. And then if you got any quandle, you can build a group, which is called the associated quandle, which is sort of, you pick the free group generated by those elements, and then you mode out, making equal what you want and what you have. Okay, you make conjugations equal to the quandle operation that you already have. Okay, that's delicate, but there's a well-known adjunction between quandle homomorphisms, which are morphisms that respect the quandle structure, and groups. And just to give you an idea, okay, you pick an exterior point, and the operation, which is tricky but it's topological, is you've got an oriented node. So B acting on A is you start from X node, B is it can be realized by a path from X node to a tubular neighborhood of your node. There, since it's oriented, you've got a unique meridian oriented like this, then you go back by B, and then you go from X node to A. So that operation, moving from B there, doing the meridian, going back an A, that's a quandle operation. Okay? And then everything goes on. We'll see where quandles appear. Okay? And now, the main goal of the talk has been roughly half an hour or even a little bit more introducing things. Now let's wind things up, okay? So now, representation varieties, AGL1 is the group of affine motions of the complex plane, okay? It's the semi-direct product of C star times C. As a matrix group, it looks like this. Matrices, well, you've got 1 and T, that's an element in C star, and then you've got A there, okay? Affine motions, I mean f of z equals tz plus A, okay? Those motions, when you write them down as matrices, projectively are those there. And let's go back to the trefoil node, okay? We spent some time to show you, well, some things that the first time that you see them, you say, okay. The representation variety of your node group into AGL1, we've already seen the presentation of the trefoil. So you've got 3 matrices in AGL1, and you want them to satisfy those 2 equations, okay? So the first thing to say there is that you've always got what we call trivial representations. First of all, A1, A3, and A2, they are conjugate, so the trace is the same, so the T is the same for all of them. And that's always going to happen, okay? Anytime that you've got a Wittinger representation of the node, those are representing meridians, and they are conjugate, okay? So the T is equal for all 3 of them. And then if you make A1 equals to A2 equals to A3, those equations are trivial, and then you get a representation. That's what I call the trivial representations, okay? They are representations that instead of representing your pi1, you're representing the abelianization. Okay, you're mapping any meridian to the same matrix. So the question is, okay, what about the other representations? And then it's an easy computation. You do that tiny computation, and then the only requirement is that A1 equals 1 minus T A2 plus T A3. It's a linear equation in T. And then you do the same for the other relation, and then you get that this is your ATL1 representation variety, representation space of your notebook. So the natural way to do here is, that's your space, and there's a natural projection, which is, okay, any representation that is common, so you can project it onto C star, any representation you map it onto T, and then if you fix the T, the fiber are A1, A2, and A3, satisfying those linear equations. And then if you write the equation down, that matrix is familiar, you get that is the solution to that homogeneous system of linear equations. The line generated by one is always a solution that corresponds to the trivial solution, and then you're gonna have non-abelian representations if and only if the rank of that matrix is 1. And then the minor there, you get back the Alexander polynomial that we discussed earlier on. Okay, this is not entirely new. Okay, the first time that you try to do this computation, this has to be known, and it's an old theorem by the Ram and Birdie. Okay, but the thing is that personal opinion should be more advertised. Okay, Alexander polynomials codify non-abelian. The language was you get an affine non-trivial representation anytime the T is a 0 of the Alexander polynomial. And then there's another result due to Hironaka, which in a complete different setup, talking about group homology, okay, said that if you pick the set of complex characters which are homomorphic onto C star of your knot group, then you've got a certain sheaf, okay, which can be naturally stratified, and then the homology group, the first homology group twisted by rho of gamma, the jumping loci, which means where the dimension jumps, naturally stratifies your variety. Okay, so in terms of group homology, there was another result due to Hironaka. So basically what I've said with the trefoil can be generalized, and I'm going to give you the general case. You've got C star sitting inside ATL1, so that inclusion yields contravariantly a projection, okay, of the representation variety of K into ATL1 onto the representation variety of K onto C star. And then the fibers are complex vector spaces in full generality using the Wigner relations as we've seen. Okay? And then I'm going to state some results. I'm not going to prove it. And in the remaining time, I'm going to show you the TQFT. But many of the things that we've been looking appear in the term of, or in the context of this fibration. So for example, if you pick a word, you ask yourself, what's the general form that any representation onto ATL1 has? You can read the Fox derivatives straight from the representation of rho onto ATL1. Okay? Then that's an algebraic affine set. It has a certain coordinate ring. And essentially, well, that's an algebra. Okay, it's not a module, but it's strongly related with the Alexander module. If you build a symmetric algebra over the ring of H1, then it can be shown that the coordinate ring is actually isomorphic as an algebra to the symmetrization of the Alexander polynomial. And then the roots of the Alexander polynomials are the exceptional locus of that fibration. That fibration is sort of a vector bundle, okay? The fiber at least is one-dimensional, but that dimension jumps over a certain algebraic subset, which is the collection of zeros of roots of the Alexander polynomial. And actually, the elementary ideals are codifying the dimension of the fiber. So the Alexander polynomial is a singular locus of a fibration. And then the fiber, which can be thought in terms of the fundamental group of those representations where M fixed in the T, has an interpretation in terms of quandles. Okay, by the adjunction we saw before, okay, homomorphisms from the fundamental group of K onto ATL1 where you're fixed in the T is exactly that space. Okay, so it's related to quantum theory. Okay, and essentially I'm gonna skip a little bit forward here. You can rephrase the construction of what you've got in terms of a singular vector bundle, which is a notion, or it calls the notion of a vector bundle such that has a exceptional locus where the dimension jumps, and then it can be restated as Burau did in terms of coherent sheaves of your model, okay? And then you get the AGL representation variety as a singular vector bundle. And then a remark, which I haven't said, computationally is a little bit harder, but all we've been doing for nodes can be extended for links. Now, H1 of a link is not generated by a single meridian, but you get a generator. I mean, if you've got that link has L components or M components, then H1 is set to the M, okay? So you can build the whole picture and repeat the same thing, but now the basis, instead of being C star, you get C star raised to M. But the whole thing works, and the singular locus is the multivariable Alexander polynomial. The multivariable Alexander polynomial, on many cases, is defined in several ways as to extend the classical Alexander polynomial, but here the definition is really, really straightforward. You do the same thing for AGL1, but now for a link, and then the fibration, instead of having C star as the basis, you've got C star raised to the number of components, and then you get a singular vector bundle again. So it's fine. And now, at least, I have, I don't know, 10 minutes, a little bit more maybe. 15, okay. Let me give you the main ideas. This is the starting point to build the TQFT I told you about, okay? Which is a TQFT to compute those Alexander particles. So now I'm gonna proceed in a different way. I'm gonna first state the theorem and then guide you element by element, okay? The two main theorems is that we've got braided monoidal functors from a certain category T, which is the category of tangles. I'm going to discuss later on and define the tangle category, to two categories, which are span of singular vector bundles and spans of complex vector spaces. These are functors called AT. Okay, those are computing the quandle representation variety, and that's computing the whole Alexander model. The idea behind, or to keep in mind, is that this is the fiber of the previous fibration. Okay, we're only looking at the fiber, and that we're looking at the whole fibration. I'm gonna focus on the latter one because it's easier, but the whole thing, all those functors can be sort of glued. Okay, and the thing of the object that you get is a singular vector bundle, and you get the span category of vector bundles. I will talk in a while what's the span category. Okay, and now tangles. Okay, a picture is much better than the definition. That guy on the left, it's a tangle, okay? It's a collection of points, and then you've got another collection of points on the top. Here we've got 7 and 7. The number of points can vary, okay? You can have 5 there and 4 there, or any number. And then a tangle is a set of polygonal arcs joining them, okay? This is a planar projection of a tangle, so you need to define so that you don't get anything weird, but the definition, the true definition is a tangle is a union of a finite number of disjoint polygonal arcs. I'm gonna consider tangles in R2 times 0,1, or in a cylinder, okay? You can think of them like this. You've got K points on the base and L points on the roof, okay? Before the picture that comes later on, it's a 7, 7 tangle, okay? And then if you wanna categorify them, the tangle category, we're going to consider those oriented arcs oriented, okay? I don't know where it is, maybe it's not there. So the points can be codified as a finite sequence of plus and minus signs, possibly empty, I'll tell you why, okay? Well, it's already down there. And then the tangle, any tangle is a morphism. It's a morphism connecting the points on your bottom, which is called the source, and the points on the roof, which is called the target, okay? So that tangle there is a morphism between those 7 points and those 7 points. And then the composition of two tangles, anytime that is defined, it's done placing one tangle on top of the other, anytime that source and target can be glued, okay? So that's a way to make tangles into a category. It's actually a finitely presented category. Any tangle can be decomposed as the composition of those tangles, okay? Those tangles there. So subject to a huge list of relations that come from Rademacher moves and certain isotropy relations of planar tangles, okay? But the idea is that any tangle can be written as the composition of those guys subject to a certain set of relations. And then the span category of vector spaces, it's a funny category. The objects are finite dimensional complex vector spaces, same thing as in the vector space category. And then a morphism between X and Y is given by a third vector space sitting on top, they're like roofs, and two linear maps, F and G, from Z to X and Y, okay? They're like roofs, so the data of a morphism between X and Y is a third vector space and two linear maps, okay? It says the equivalence class, okay? Because you're gonna declare two spans equivalent anytime that you compose with a isomorphism. So that's the picture. You've got here F prime and G prime, that's a span between X and Y. And then if you compose with an isomorphism, you get another one, F and G, and you're gonna declare those two equivalent. Okay, so that's the span vector category, the category of vector particles. And in this category, composition is done or is dealt with the fiber product. You've got here a morphism between X and Y, another one between Y and Z, so those four maps, and then the composition is that vector space, which is the fiber product of Z1 and Z2, and you get a map there projecting onto the first factor and a map there projecting onto the second factor. So that's the way you compose spans. So it's a category that generalizes the usual category of vector spaces. And now, how is the functor built or how it's written, okay? On objects, I didn't mention it, and it's really important, we have nodes in mind. Let me go back. Nodes as tangles are endomorphisms of the empty set. It's a map between the empty set and the empty set. So we do it for tangles, then we got the invariant for nodes. And then on objects, the definition is weird, but let me guide you through the definition. The image of the empty set is going to be the zero vector space, and then the image of a set of points is going to be C raised to the number of points that you've got as the source of your tangle, okay? So on objects are collections of points, so it's C raised to the cardinal of the number of points that you've got. In abstract terms, or in representation theoretical terms, you've got the free quandle. You can think about groups if you prefer. You've got R2 minus a set of points, so you can talk about the fundamental group of the complement of those points, and that's a free group, okay? And mapping that free group onto AGL1 and fixing T is the same as giving the off-diagonal entries. So representing that quandle, representing the fundamental group of the complement of the base, is prescribing those n complex numbers. You've got free quandles, you've got free groups, okay? The idea is the same. And then, given any tangle, okay, you can consider that tangle embedded in R2 times 0, 1, and the fundamental group of the complement representing that into ATL1 is the same, and fixing T is the same as that object, okay? You can define the quandle of the tangle T using, as I told you for nodes, you can do the same trick for tangles. You can finally present it using a planar projection, and then that's the space. And Y spans, you've got the boundary of the tangle, the point there, you get inclusions of the quandles of those points inside the quandle of the tangle. Or if you think about the fundamental group, it's the same thing, okay? The inclusion of, we'll see an example in a while, okay? And then if you got those inclusion maps, when you consider representation spaces, it's contravariant, so you get a map from the representation space of the tangle onto the set of points on both boundaries, okay? And that's a span in the vector space category. It can be shown that those are linear maps, and that's a Cn, C to the number of points, and C to the number of points. So everything moves to linear maps and complex vector spaces. And then there's a lot of things to prove and show, okay? I won't get into the details. The functor is well defined, you have to check several things. It's monoidal. You've got a monoidal structure you can, anytime that you got two tangles, you can put one aside the other and get a new tangle. That's that tensor product there. And then there's also a monoidal structure. Instead of using the tensor product, the direct sum also satisfies the properties of a monoidal structure, so it respects those structure. And then anytime that you've got a node, it's a tangle between the empty set and the empty set, so you get a span like that one. So everything is codified there, and that guy there is the AGL1 representation variety, which we've seen that computes the Alexander norm. And then you can extend this to link, and then you can, instead of fixing the T, do everything at once for singular vector values, okay? And then to end the talk, okay, I wanted to show you an example of how things look in the span vector category, okay? This is one of the generators, okay, of the tangle category. That's a positive crossing. So this is a two tangle. We've got 2 points on the source and 2 points on the target, okay? And then the fundamental group of R2 minus those 2 points is a free group with 2 generators. The fundamental group of the tangle, that tangle sitting inside R2 times 0, 1, has, this is Whittaker again. You've got one loop there, alpha 1, one loop there, alpha 2, and then you've got that alpha 3, which is conjugated to alpha 2 via alpha 1. So it's the Whittaker relation we showed and used for the fundamental group. You can do it to compute the fundamental group of the tangle. And then, what about the maps? Well, let me, sorry, oops. Yeah, spoiler alert. Let me go back. There I am. That map of including those 2 loops there, those generators, inside the fundamental group of the tangle is the identity, because of the way we've chosen generators for the fundamental group of the tangle. Okay, so one of the maps, the inclusion of that boundary over the top, is the identity, and then the inclusion. Yeah.
Why do you take R2 times 0, 1?
Because anytime that I say the fundamental group of the tangle, I'm thinking of the tangle sitting inside R2 times the interval. The tangle sitting on a cylinder, and the fundamental group is the fundamental group of the component.
And you take the points in the border of the cylinder.
Yeah, that's sitting inside a cylinder. So you've got here it's R2 minus 2 points.
Okay.
Up there you've got R2 minus those 2 points. Those are the fundamental groups I'm talking. And the fundamental group of the tangle is that guy sitting inside the cylinder, the fundamental group of the component. So the inclusion of the bottom part is the identity, because that one and that one, you basically map generators to generators, and the map above, you get a generator there and a generator there. That one is alpha 2 conjugated by alpha 1, and that one there is alpha 1. That's the map I was talking about, okay? And then when you compute representations, you get that that map there is the identity, and the other one, when you represent those loops, is a map from C2 to C2, which is called F plus, which is essentially the relation you get from Whittaker, and then the other one, which is the identification that we're making. So that's the image in span of vector bundles of that tangle. And then the trefoil was the motivation. Let's apply everything to the trefoil, okay? Now the trefoil is going to be, can be done like this, can be represented as the closure of a certain braid. You pick the X plus, you compose it 3 times, and you get that braid, okay, that tangle, and then closure means in this context closing the whole thing so that you get a knot, okay? So now, what's the image of that braid, that X plus cubed? When you compute this span with the identity and the F plus, it's really straightforward. It comes from the inclusion of the usual vector space category inside this span category. You get F plus cubed, which is that matrix there. And then this closure, okay, it can be shown, essentially, you decompose this as, that's the X plus square cubed, and then you've got those arrows there, and then closing means closing with those guys, that one there and that one there, and above those 2, okay? And then since you have full control of the spans of those guys, you do it, and it's the fixed point set of that map. So when you take that matrix and then you compute the fixed point set, is the kernel the fixed locus of that map, the kernel of that matrix, which is the one from before, or there's a typo where it should be a T. And then the line generated by 1, 1 is always invariant, and then the dimension jumps if and only if, again, you get the Alexander polynomial, but now from an entirely different path. Is this new? The answer is no. Okay, there's a similar construction made for braids. There's a very well-known and thoroughly studied representation of the braid group called the Burau representation, and the first one was the closure of a braid. So what I did using this functor, or the functor AT, was something that was already known for the braid group. The thing is that we can apply it not only to braid, but to any tangle, and that's entirely new. When T is a braid, those AT, the image by the functor, can be taken to be a basic span. A basic span, that's terminology, but it's a span of that looks like this. You've got the identity there, and then you've got a different map. And those are easy spans. Actually, you can check that those spans define an immersion of the vector space category into the span category. So somehow the functor also generalizes the Burau representation, and that part is neat. And there's a formula for the Alexander polynomial connecting the Burau representation and braids. We recover that formula from our functor. And basically, from this, we're working on several things. We're proving some classical results using our functor. We're working out closed formulas using the TQFT for the Alexander modules and polynomials of families of nodes. Okay, giving you, since it's very explicit and you're using complex vector spaces, it's, well, some work needs to be done, but it's really straightforward to produce formulas of this type. And then working with many other topics related with coloring, the arithmetic of this bundle, and working with other groups, fibers, and many things. So this is it.
So maybe you have told it and I haven't heard it, but so in general, when you construct a TQFT, you want to end up on the category of vector spaces, or more generally of modules. So the span category is just an intermediate step. So in this situation, why do you end up on the span category? Why is it important to end them?
Well, why is it important? I'd say that yes, the classical setup, you start with cobordism and then you end up with vector spaces and the tensor product. And here, instead of why we're forcing, it came natural, I'd say, okay? We have the tangle categories. We were understanding, the first step was finding that the AGL1 representation variety was essentially encoding all the Alexander polynomial. And then when we tried to use what we knew about breaking a representation varieties into pieces and gluing representations, that's how we ended with the span category. Because anytime that you're building or you've got a node, that's what I did, okay? You had, I'm an awful node drawer, okay? But this one's easy, okay? That's a different version of the trefoil that we did there. Breaking things into pieces and then gluing representations, they're representing those tangles, and the way you're gluing exactly as you do for cobordisms land you on the span category. It's the natural thing to do, in which you can glue representation and then get the whole picture. So instead of, it was the other way around. Instead of forcing things, when gluing representation, is quite natural to end in a span category.
Yeah, but I mean, when you do it on cobordisms, for example, you do that, you do the span,
yeah,
but then you also do the quantization.
That's right.
So why, in this case, you don't do the quantization? What's the difference between these cases?
He's raising his
I can answer this question in one.
No, go on.
So from my point of view, the point is the following: you need to quantize in the case that you want to compute some invariant of motivic nature, meaning that I want something that is additive for this union. In this case, the Alexander invariant has not this property. So if you apply a quantization, a final factor, you will get something else. But you don't want to get something else. You want to go. This actually means that Alexander invariant is not as difficult as the Jones polynomial, because the Jones polynomial requires a whole factor to be quantized, but the Alexander polynomial only requires half of the factor to be quantized. But really good question.
And much clever answer than the speaker would think. Yeah.
When you cut the knot into pieces in tangle,
Mhm.
so in each tangle you are computing the fundamental group of the tangle.
That's right.
So when you get the whole representation, you cannot get something finer than the phi one.
That's right. No, we're recovering everything. Well, yes. I mean, you're not getting. I mean, we're not getting anything stronger than the Alexander model already had. Okay.
Does it make sense, for example, in each piece, instead of computing the fundamental group, considering the generalized groups like E2 and because these are complete invariants.
What do you mean by complete? Okay.
The ones you get from the quandle.
From the quandle, yes, but the not quandle is a complete invariant, but somehow we're representing it onto some other quandle, which is much easier, which is the Alexander quandle. But yes, the question makes perfect sense. Instead of representing the not group or representing the quandle, I mean, there has been certain amount of research about quandles and its representations. And the thing here, I mean, it was already known that the Alexander quandle had to do with the Alexander polynomial and so on, but this, seeing the whole picture as a single geometric object, which is a representation variety, and gluing things in order to get the TQFT, is the new thing. But yes, you've got the not quandle, which is finer, and that's striking, at least for me, than the fundamental group. The thing is that it's also codifying not only the not group, but the peripheral subgroup. That's what lies behind the not quandle. And yes, we're representing it into something simple. The theory of the factor is defined in terms of quandles, but by the injunction I showed, you can define it in terms of the fundamental group onto AGL1, and then you're fixing the T. If you don't fix the T, you get the singular vector bundle picture that I was the general statement about the other one. And by the way, for braids, it was already known, but it wasn't done like this using other tools. The cool thing of the new thing is that we can do it for any tangle which is not a braid. A braid is when everything flows upwards and then every strand has the same orientation, and then you've got here and there the same number of points, N and N.
Questions?
At the end, you spoke of the possibility of extending to other groups. Which group do you have in mind?
SL2, okay, which is the main ingredient, okay. I mean, it's not going to work in the same way, but let's dream. And this trick of having that C star sitting inside AGL1, if you try to extend it to other cases like, I don't know, AGL2 or whatever, maybe things work out, but it's entirely. Of all those points, is the one that we haven't tackled yet. The other ones are work in progress. So it's the one that, yes.
So when you introduce it for derivations from a presentation of a knot group, it does not depend on the presentation, right?
No.
This is a specific of knot groups because of the way relations are.
No, Fox derivatives can be, I mean, this whole thing can be approached from, no, I mean, it's not specific of, you can define that Jacobian and Fox derivative for any finitely presented groups. So you get a Jacobian and you do the whole thing.
And it does not depend on the.
That doesn't depend on the. What it does depend is that you've got within the relations, so you can work things out in quite an easy way, and then you can extract a lot of information from there. But no, Fox derivatives and the whole thing can be approached group theoretically without any reference to not groups, using it for finitely presented groups.
I have one comment and one question. So the comment is actually your work is very interesting, but In principle, his work is very interesting, but you are understanding homomorphisms of the not quandle into a fixed group, that is in this case AGL1. The Tanaka duality says that if you know the representation category of the whole group, then you know the group itself. So the complete invariant will be representations into any group of your not quandles. Just to mention that in this case, AGL1 is the easiest possible group that you can cook up that is non-abelian. So the easiest possible group you can take quantizes the Alexander polynomial. So there are plenty of room to improve, And the question is, can this be extended to 3 manifolds minus nodes? Can you do something similar, like saying, okay, I have a 3 manifold, I'm removing some embeddings of S1. Can I construct some kind of TQFT computing the same guy, like the representation variety of the fundamental group of the knot complement?
My disclaimer 1, he wasn't here, but he's a co-author, okay? So it's his work and my work. So no. Okay, in case anyone was wondering.
He's the expert in knots. He's the expert
No
in
way.
knots theory.
And then disclaimer number 2, that's a great question, and I mean, you know the way it's worked out. In principle, maybe, but the fundamental group of a 3 manifold can be pretty wide, okay? There's some restrictions, so building the whole thing, I mean, you know how this works out. From examples, we build the whole castle, okay? Starting from tiny examples and then generalize it. And here it would be the opposite picture. But maybe, I mean, of course, you can decompose 3 manifolds in a certain way, and then, yes, geometrization and all that stuff.
Exactly.
But things, I mean, I'm not an optimist man. So I'd say that interesting question, but hard work. Yeah.
But at the end of the day, the thing that is underlying is safer than Kaplan.
Well, that's
because it's the reason why it's a functor.
Yeah.
Because safer than Kaplan says that gluing is having a pullback. Yeah. So it's safer than Kaplan.
There is a paper where
that's a bad way to sell what I just explained. But yes.
I think by Catabria and Santanes, and they decompose the 3 manifold in surgery diagrams, and they compute the quandle by taking from the diagram.
That's right. I mean, I don't know if it's the same paper. There's a Categorifying paper which we quote, which we realize later, but building the whole thing is that yes, you get your knot complement, and then they build a quandle. I mean, they factor or they build a functor from the tangle category to the quandle category, and then somehow we're representing that factor.
That's one of the papers, and then she has another one. So they describe the manifold in terms of surgery diagrams with the knot, and so by looking at that diagram, they compute the tangle. Maybe it's
yeah, the first one I have read it, yeah, and the other one we can look at the reference model, something.
More questions? So then, thanks to Javier for this extraordinary talk.
No digas eso, que no, yo no sé de nada.
Yo solo puedo categorías.
Yo no sé de nada.